first, I will offer in some information to help you guys understand how to jump from the traditional ANN to deep learning, that is use of deep neural networks. Then we'll take a look at two popular deep neural networks. One is CNN, which is short for convolutional neural network. The other one is for RNN, that's for recurrent neural network. CNN is good for dealing with image data. So when we have relationships between the different points in the sample in the space. And RNN is good for handling the time series data. So when you have, for example, you record something, you speak something, we know that the next time point is relevant to the signal at previous time points. Finally, there's also some practical skills. You can find these skills. Some of them are very useful when you're implementing deep learning. So we will not spend too much time on this, but if you are interested, please go to the book chapter. First, from ANN to DL, we will first take a look at the history to see how ANN was developed from the very beginning and all the way to deep learning. And we will talk about the key advances in this process. Next, for convolutional neural networks, CNN, we will take a look at a few things that you did not see in the shallow neural networks. Let's, for example, the convolution layer, the ReLU, and the pooling layer, and what are the meanings of these things, and what are the mathematical operations, especially for the new layers, the convolution layer and the pooling layer, how to do the propagation. They're not the same as the fully connected layers as we introduced in the previous lecture for shallow ANN. They're different, sometimes much different. Next, for RNN, we'll take a look at the structure of an RNN. There are different structures. We'll take a look at one classic one. Then we will see for that classic RNN structure how we can do the back propagation, including both the forward pass and the backward pass. Finally, for practical skills, here's just very briefly mentioned what you possibly want to look into. First is initialization. And this is one key thing that enabled deep learning. The other one is the solvers. We said that when we're dealing with very simple machine learning problems, sometimes we can get analytical solutions. Sometimes we can use for example, a commercial package, optimization package to solve the problem. But in a few cases, just like deep learning, now the models are super complicated. We are talking about millions and billions of weights, model parameters. For such complicated models, we need to use optimization, and we need to use methods such as gradient descent. For that one, we're now talking about solvers or optimizers, which can be used to solve such complicated optimization problems. When you're doing the deep learning, and for example, if you want to use TensorFlow, PyTorch, or Keras to solve a deep learning problem, sometimes you are required to specify which solver that you need to use. And for some solvers, you even need to specify what parameters you will use for that solver. Those are hyperparameters. So in order to use or specify those solvers, you need to understand what they are. And this is something you will also possibly want to look into if you want to get a decent understanding of deep learning. First, let's take a look at the history of ANN and DL. In one of the previous lectures, we talked about the history of machine learning in general. Here is very similar. You can also see that the history of deep learning is actually highly related to the history of machine learning. We also have three waves, went up and down. You can see that everything started from 1943. We got that famous MP model. That's how we describe the biological nerve using mathematical model. That's one of the things that starts the whole connectionism. Then after that, there's one time when the connectionism was blooming. People got interested in it. And then in 1957, we got this perceptron. That's what we talked about before, only two layers, very simple. And in 1960, back propagation was first implemented, but not for deep ANN, is for control purpose. Then in 1969, they can see that that's the first peak. And that peak, one thing happened is that someone criticized about the potential and feasibility of ANN. They believe that an ANN is not good, but it cannot be used to solve nonlinear problems. So people believe that that's something too simple, it's not realistic, cannot help us reach general artificial intelligence. But after that, in 1971, backpropagation was first coded in computer. Then we got the first AI winter. Right after the AI winter, in 1989, you can see that now the CNN was first implemented. Sorry, that's 1980. I apologize. And then in 1982, RNN, that's another significant deep learning architecture, was implemented. And then in 1985, Boltzmann machine, that's also a very significant architecture or technique for deep learning. It enabled the training of deep neural networks in the early days. In 1986, that's kind of the bottom, backpropagation was implemented for a neural network, and also the restricted Boltzmann machine was proposed, something right up again in around the early 2000. Then in 1989, something called the universal approximation theorem was proposed. This one tells us that we can get neural networks that are complicated enough that can help us solve any problem with any levels of complexity in theory. So that kind of gives us the confidence so that if we can deal with very complicated neural networks, we can solve anything, any complicated real world problems. Then in 1991, that you can see second peak, another major issue was reported. That's the vanishing gradient issue. So for this one, researchers found that if the layers of neural network get high, that means we have too many layers. Then the problem is that when we do the backpropagation, the gradients will get smaller and smaller as we go backward. And if we go beyond 3 layers, 5 layers, we will see that the gradients are approximately 0. So that cannot help us to update the weights in those early layers, first layer, second layer. So because of that, that discouraged many people, because people find that we cannot solve this vanishing gradient issue. That means deep learning is not feasible. Even we know that if the neural networks can be complicated, then we can solve any problem. But we don't know how to train those complicated neural networks because the gradient, they will disappear as we go backward beyond like 3 layers. Then after that, we have a time when statistics was blooming. This steps into the area of machine learning. In the year of 1997, one very popular RNN architecture, long short-term memory, or LSTM, was proposed. Then after that, there's a time when support vector machine was predominant. Then next significant time point is the year of 2006. In this year, one significant paper was published in Nature, and in this paper, the researchers proved that training deep neural networks is possible. And the tool that they use is called deep belief network. Then after that, we entered a time of fast development for deep learning. Especially in 2008, GPU was promoted as a very good computing resource because when we are training the deep neural networks, we have a few major barriers. One, as I said, is the vanishing gradient problem. Another problem is that we don't have enough data. So that issue was kind of gradually solved by the big data. We're getting more and more data. And the third major issue that we got for enabling deep learning is that we don't have enough power. And previously we used CPU. For CPU, they're not good enough. GPU is good because GPU kind of put a lot of small cores together, let them do very simple tasks parallelly. And what's cool about that deep learning is that many of the training computation can be parallel. So that in that way we can use GPU. Then in 2009 we got that image nets. So you can see that we made some breakthroughs in data as well. In 2010, one very significant thing that also helped solve the vanishing gradient issue is the Xavier initialization. Then in 2011, we got another breakthrough. That's the ReLU activation function. This one can also help us solve the vanishing gradient issue. Then in 2012, one of the most famous deep neural networks is called AlexNet, was proposed and it was implemented and attended that ImageNet competition. It did not win the competition, but it quickly attract attention from computer vision. So people saw the power of deep learning. And after that, we keep making advances. For example, in 2014, one thing is that we got a tool called GAIN, and also we have new, better deep learning architecture. That one is the Google Net. In 2014, we have the AlphaGo, which deep learning also contributed to. And in 2015, batch normalization. This is another significant tool that can help us address the vanishing gradient issue. And after that, for example, 2015, we got the residual network, or ResNet. That's also a very significant neural network. And we also have some other things, for example, the RCNN, faster RCNN, that is good for object detection. They're not dealing with the whole image, but just zoom in and look at one specific area and identify the object in that area. One similar thing is in 2016, we got a YOLO. That's another tool. It's very faster, and it can help us to identify, for example, objects in transportation applications. So you can see that this is kind of the history of deep learning. And the key things, they were proposed at different times. Some of them they're proposed very early, but back at that time, they did not make waves just because some of the other things which are needed for their occurrence was not available. And again, one more thing. So to move from and deep learning, a few things. First is we need to solve the vanishing gradient problem or issue. Second, we need to have enough computational power. We need to have good GPUs. Or maybe in the future, we will come up with better computing devices. And third, we want to have good data. So we have very good databases so that everybody can use. Then next, let's take a look at the vanishing gradient problem. And this usually happens with ANN with 3+ layers. Previously, we got an issue because we used activation functions such as sigmoid and the parabolic tangent function. And in the upper subplots, it shows the two functions. And in the lower subplots, actually, it shows derivatives of those two functions. Because we want, in the previous lecture, you can see that in order to get a gradient, we need to keep getting the derivatives of the activation functions, right? For each layer, when we go back to each layer, we need to do it once. When you go to the next layer, you need to do it another time for another activation function. And usually the gradient of that layer need to be obtained by getting the product of all the derivatives of all the activation functions. And to show that, here on the left, I give you two examples. They're not very strict examples. The idea is that if we have multiple layers and each layer only have one neuron, and x is the input. Here are two examples. In the first example, x is 0.1. The other one, x is 100. So I want to give you guys an idea. When we have the input that's very small and very big, what can happen? And if we have one neuron, we use sigmoid as the activation function. First, we go forward, then we go backwards. And if we don't consider the weight, just consider what the gradient could be without any weight. Let's assume that the weight is 1. What's going to happen is that you can see that the bottom here, the 1. That means if we have a gradient of 1, in the last layer, if we go backward, the second and last layer, that gradient will become 0.115 about. If we keep going, the third last layer, we will have a gradient of 0.011. So you can see that it's very small, right? It's just 1% of the gradient in the last layer. If we keep going backward, the fourth last layer, it will become much less than 1%. If we keep going, basically, it will become 0. So you can see that the gradient disappears. If we do it in this way, what's going to happen is that, if, for example, if you have a neural network with 10 layers, as what I showed in these two examples, you go forward, then you go backward. You go forward, you make one prediction. The prediction is not the same as the true label, so you get the loss function, right? Then based on the derivative of the loss function with respect to the weight that you want to update, you can go backward layer by layer. Then we update the last weights in the last layer. The weights, the gradients are very high. So you have learn rates, so you can update it very well. But you keep going, as you go beyond 3 layers, you will find that the gradient is approximately 0. So there will be no update on the weight. That means the back propagation will not take effect in those early layers. So that is the problem. When I was introducing the history of deep learning, you could see that I mentioned a few key techniques that we can use to solve this vanishing gradient problem. And again, let me summarize the key enabling innovations, why we can move from ANN to deep learning, and why this transition did not happen early. Here are a few key things. First, we need to have better data. We need to have, of course, we need to have more data. In classic machine learning, you can see that we are playing with a very small amount of data, right? We are playing with 10, 20 samples, and each of them may only have a few attributes. But now we're dealing with complicated images. So one image is a sample, and one image, you can imagine how many numbers you have in one image, right? Typical images, they have 3 channels, RGB, and each channel, for each pixel, it has one value between 0 and 255, and that will specify what color it should have for that channel. So let's say that we are talking about big images, even teeny tiny ones. They're 100 by 200. You can imagine 1 by 200. That's how many? 20,000. And 3 channels. That's 6,000. That is huge. One sample is like that big. So that is the first thing. And also for data, we need to have better pre-processing techniques. And because in the previous, when we were dealing with the classic machine learning, we only have very small amount of data, so they're easy to be treated. But as we move from those simple data to complicated data, usually we need to have way much more complicated pre-processing techniques. We also need to do the normalization. When we're doing the shallow neural networks, we also talk about this depending on the activation function, because they will squash the input in a small region. So accordingly, we also need to squash our labels in a similar way so that they will be comparable. Otherwise, your output prediction will always be between 0 and 1, but your true label is between 1 and 10,000. So that would help. Actually, we cannot train a network because of that. So normalization is also significant. Second is better weights. Especially, we need to have better initialization problems. And actually, in the early stage of ANN, people did not realize the significance of initialization. And in recent years, people got aware that initialization actually determine whether we can solve the vanishing gradient problem easily. So because of that, a lot of new initialization techniques are proposed. The next something, we also have pre-training. You can train the network with some data, then you can move it to different problem. That's all this concept is also closely related to transfer learning. Next is better network structure. For example, one key thing is activation, as I showed on the previous slide for that vanishing gradient problem. You can see that the classic sigmoid, hyperbolic, tangent, activation functions, they caused issues. One major issue is that as you go to the two ends of this, you can see that the gradient is really small. So we need a better activation functions. Also, we need better architectures. It's very interesting that introducing the history, you can see that CNN, they were proposed a long time ago. But back at that time, we didn't have very good tools for training those neural networks to get the performance that we want. But now we have the power. And we also have new things as TM and more recent and network in network and residual network. And in recent ChatGPT, we also have new things such as self-attention. So those are the people are, we are trying to looking for better structures or better structure innovations that can help us to get better deep learning results. Another one is the better solvers. This is not a class, not an area of deep learning, but as I said, when you're doing the training, when you are using some tools for implementing deep learning, you need to specify the solvers. So we need to know what's the meaning of the solvers and how to determine the values of the hyperparameters. And also, when you move from deep learning, we also need to deal with the overfitting issue. And we know that we got overfitting issue is because our models are too complicated compared with the data, right? Now, even we have very big amounts of data because our networks are getting more and more complicated. So for deep learning, it's really easy to get overfitting issues. And one classic solution to that issue in deep learning is to use better regularizers or try to take advantage of regularization. And we also, of course, we have better computing resources, GPU and parallel computing. Next, let's talk about the convolution neural network, CNN. Before we get into the details, let's take a look at one example. This is the AlexNet that I mentioned. This is the architecture or the structure of it. So you can see that here, this is kind of the inputs. And this is the shape of it. This is the image. One has a width of 227, height of 227. So 227 is the number of pixels in that image. And 3 is the channel. maybe 3 channels. They're in charge of 3 different basic colors. And then so you can imagine this as a 3-dimensional arrays. So it has 3 dimensions. Not 2D anymore because of the channels. If the image only has 1 channel, then you can imagine it as a 2D array. The height of the image is just the number of rows of the array, and the width of the image is just the number of columns of the array. Then we will enter this image as the input of the AlexNet. First layer, you can see something CONV, that means convolution layer. And the convolution layer is different from what we talked about before, FC. FC means fully connected. That's what we learned before, the fully connected feed forward, ANN. And we'll talk about how to do the convolution layer. To this one, we need to specify a few things. The first number, 96, is the number of the convolution kernels or features we have. So here we have 96 in the first layer, and 11 by 11, that is the size of the kernel. For a kernel, you can imagine it as one small window. So what we do is that we just put the window on like one part of the image, then slowly move the window, so we can get if we look at our eyes, we'll see different things. And after that one, we will see that the input size, the shape of the input will become 96, 55 by 55. So 96 is also the number of kernels. That means if you do that, the original image will turn into 96 arrays. And for each array, now the image size is not 227 anymore, but the width and height both become 55. And if you want to do that, we can do it later on. If you know how the convolution works, you will see why the signs will change from 227 to 55. Next, we have another layer called a pooling layer or pool layer. Here's one type of pooling layer. It's called max pooling. For this one, what we do is that we do the down sampling. The original images, they're too complicated, right? They're huge. And if you think about what we did in the previous machine learning topics, we're dealing with very simple data. Now one data sample is so complicated, and we have large number of images, data samples. So in order to solve that, in order to use the fully connected layer, just like what we did in the shallow neural networks, we need to do down sampling. So the size of each sample will become smaller and smaller. So here we use the pooling, is a 3x3 pooling. For this one, 3x3 is the size of the pool. Later on, we will see what that will do. And we have another thing called stride here. Stride, that is that both convolution kernels and the max pools, they can be visualized as the window. So if it's a window, then it should have shape, right? Here, the shape is 3x3, 5x5. And also, when we are sliding the window over the image, we want to determine how big a step that we will make for each movement, right? Next. And the distance between the neighboring window locations is called stride. Next, after pooling, the size becomes 27 by 27, and we still have 97 arrays. And we keep going. Next, we have another convolution layer. For this one, we have 255 convolution kernels, and each kernel has a size of 5 by 5. Here's another concept, padding or pad. For this one is that in many cases, when we put the window on the image, sometimes we can start from right on the edge of the image, right? But sometimes that's not working. So what we do is that we can use the space out of the image and we add some empty space there. That's called padding or pad. And here pad means each pad will have 2 pixels or 2 numbers. And after that, we will keep going. You can see that another max pooling layer with the size of 3x3 and a stride of 2. And after that, we will get data with the size of 256 by 13 by 13. Again, this is a 3-dimensional array, and it has, you can imagine that we have 256 2D images, and each image has a shape of 13 by 13. That's the width of height. Keep going, we will get here. You can see that we have how many convolution layers we have? 1, 2, 3, 4, 5, right? So we let it go through 5 convolution layers. Then we pass the last max pooling layer. We will get the output 256. That's, you have 256 images, and each of them has 6 by 6. Next, what we do is that we let it go through the fully connected layer. Before that, we usually do the flattening. We did that before, and you can see that this will give us an output of this 4096. So that's the number. It's a 1D array, another 1D array. So go to 3 fully connected layers. Eventually, this can be in this case is for a multi-class classification problem. We need to classify the images into 1,000 categories. So this is the CNN. And in this example, you saw a few key concepts. For example, what is convolution layer, what is pooling layer, and what's the sizes of different things, and how the shape of the data is changed as we move through different layers. Next, let's take a look at convolution theory. That's what happens when we're doing convolution. And if you took like a course like a signal processing, you possibly have heard convolution before. But at that time, you possibly learned something like this. This is the continuous form of the convolution. So you can see that it's integration. You can understand it as we put a moving window on the original function. And every time that a moving window is something that can magnify or scale or distort the original image using some weights. So you use that window to look at the original image. That will give us different things. So that's what a convolution does. But here we are dealing with discrete numbers. We're talking about arrays. We are not talking about continuous functions, right? So now we need to use discrete form of convolution, and the mathematical formulation is like this. But this may still be a little bit too complicated to understand. To get a better understanding of it, let's take a look at the example shown in this figure. On the left, you can see here we can imagine this as an image, right? One channel, and what's the size of it? Width, height, what's the size of it? Of this image? What's the shape of it? 3, 4, 5, 6, 7. 7 by 7, right? It's a teeny tiny image. And for each of them, we can see that it has number either 1 or 0. So here we want to use a kernel here. Let's call this one I, or input. Call this one F. You can see that for F, some people call it a neuron, some people call it filter, some people call it kernel. So let's call it, it's filter here. F. F, we apply this F, this convolutional kernel, to the original image. And here we use a stride of 1. So there's no padding. So that means the edge of the filter will be the same as the edge of the image, right? We will not let the kernel get out of the image. So pay attention to this. You can see that what's the size of the kernel in this case? 3 by 3, right? This is 3 by 3 window. So we put it here, the red one, the first one. And what it does, what the convolution does, in a very simple way, you can understand it as a weighted summation. So the numbers in the filter or in the kernel are weights. So we use these weights to get the weighted sum of this area that is scanned by the kernel. You can see that the first red area, 3 by 3, we want to get the weighted sum. So what do we do? First element 1 times 1 plus second element 0 times 1 plus this one 1 in the first row and the third column, 1 times the 1 in the third row, and the first row and the third column, that's also 1. So we're doing that. Weighted sum is what? It's 4. Then we finish the first one. The first weighted sum will be the first new element of the output. So for the second one, then we slide the kernel to right. We use a stride of 1. So then the next step, the kernel will be focused on another 3 by 3 area, right? That's the green area, right? Could you do it yourself? What you will get? What is the weighted sum? Green area. Yeah, do this. Don't look at the answer. Try it yourself. The weighted sum of this one is just a dot product. You multiply the corresponding elements, then get the summation of all the products. So try to do it. I know it's very simple, but do it. Make sure you can get the answer. Use a pen. It's very simple. Did everybody get 3? Okay. So now you can see that, this is second winged. That's the second focused area. So for this one, we get a 3. That would be the second element in the output. So we keep moving the kernel depending on the stride that we specify. We will getting new elements, right? And in this case, you can try how many elements we will get in the first row. How many elements we will get in the first row by applying this kernel, 3 by 3 kernel, to this original 7 by 6, 7 by 7 image with the stride of 1 and a padding of 0. How many? First one, right? Yeah. 1, 2, 3, 4, 5. There you go. Then you guys can go back to that Alex example that I showed. You can see that at the very beginning, the size is 227, right? Then it got smaller. The reason is that we did something like this. And what is the size? The size of the output depends on the size of the kernel, the stride, and the padding, right? So you can do the calculation yourself. And we keep doing this. You can also tell how many elements we should have in each column. It's also 5, right? do it in the same way. So this is convolution. And you can see that one key thing of this convolution is here, what I showed, is a dot product between I is the input and F, that's the filter. Sorry, not feature. I made a mistake at the very beginning of this lecture. F is for filter or kernel. And if we want to go forward, let's say that if we are talking about a deep neural network, in it we only have convolution layers. What's going to happen is that let's take one layer out as an example. You can see that if we want to go backward, that's the blue lines and equations. We go forward, we just need to do one thing when we are talking about convolution. That is just I dot product F. And we keep going. Since this is O is not a zero, so input, we apply the kernel to it, then we get O, the output. And for the layer that we are considering, for example, the layer in the middle, we call it layer N. The next layer will be N plus 1. The output of the nth layer, ON superscript N, will be the input of the next layer, right? That will be I superscript N plus 1. So that is how to move forward. That's similar to what we did before. What we did before is W dot product I, right? That give us the output. Oh, we also need to have that activation thing. Here we don't need to worry about activation, so it's even simpler in the forward path. Backwards is a little bit more complicated. Here we want to update the weights, so we need to think about it, what weights we want to update. Now we don't have what are the layers we're talking about. Previous layers, that means we have neurons, we have the W in it, right? Now we are talking about a convolution layer. In the convolution layer, we only have kernels, right? And we need to use multiple kernels or filters. And for example, in the first one we saw we use 96 kernels. So 96 kernels, if the size is 5 by 5, that means we have 96 2D arrays, each of which has a size of 5 by 5 as they contain the weights. So each kernel contains 5 by 5, that's 25 numbers as the weights. We will need to update. When we're talking about it, we want to update the weights of a convolution layer. That means we need to update the weights of all the filters, right? 5 by 5, 3 by 3. Can everybody understand this? Now we're not talking about neuron anymore, we're talking about filters. So we want to update this F, this filter. To do that is the same thing. We still use the gradient descent method, and the how big step we want to make depends on two things. One is alpha or eta, that's the learning rate, and the other one, that's that gradient or derivative of log L, that's the loss function with respect to F. So it is the same thing. But to get partial L, partial F, we need to do a few things. If you do, later on I will show you how to do this. So to get partial L, partial F, if you do the deduction yourself, you will find that it equals I dot product, then partial L, partial O. O is the output of the current layer. And the partial L, partial O, we need to calculate this one so we can get a partial L, partial F. Then partial L, partial O, how to get it? It's get from, actually this is the complicated part. It comes from the previous layer, partial L, partial. So the current layer, partial L, partial ON equals partial L, partial I, N plus 1. Again, that is because the output ON of the current layer N equals the input of the previous layer, right? So we just keep going backward. And in the last layer is special because in the last layer, this thing, the partial L, partial I can be calculated. We only can get that in the last layer. Then we go backwards. We can get all the partial L, partial I, or partial L, partial O. And that can be used to calculate partial L, partial F. If we get that one, then we can update the weights of the kernels. And let's take a closer look how these things were obtained. Now, why we have this. For example, y partial L, partial F equals I dot product, partial L, partial O. So this is the forward pass. Forward pass, again, the convolution of two things. I is input, F is output. It's just I dot product F. And if we use the example, for example, if the input has a shape of 3 by 3, we use a very simple example, try to get a clear understanding of the process by playing with the small number of numbers. Then F only have a shape of 2 by 2. And output will give us 2 by 2. So how we do that? Take a look. This is how we do it. It's dot product, right? You know how to do it. So if we do it, you will get 011 equals this, 012, 021, 022. Again, you know why this is 2 by 2, right? Again, this is the window. First one, second one, third one, fourth one, right? So first one, second one, third one, and fourth one. That'll give us 011, 012, 021, and 022. So we don't need to remember this. I want to just show you guys how we can get this. Just give you guys an impression. Then with this, let's talk. So that's the forward pass. Now let's talk about the backward pass in the back propagation. As I said, we need to get two things. One is partial L, partial F. The other one is partial L, partial I. We still use the chain rule that we used before. Partial L, between partial L, partial F, partial, we have the O. So we add O in it, and for I, it's the same thing. And to do that, to get this, here, we just give you guys one example. For example, partial L, partial F. How to do that? Go backward because we need to get a partial L, partial O, then get a partial O, partial F, right? For partial O, partial F, we just need to go back to the previous slide. You know O is a function of F. So you go to the derivative of the, O with respect to any F, you will get I, the corresponding I, right? That's why, oh, sorry, here, there's one mistake. Here, the X should be I, not X. There's a typo here. I11, I12, and you write everything out. You write all of them out, and then you can write everything in the algebraic format. So use as arrays. If you do that, then partial L, partial F, that's this, and will be equal to another convolution operation between input I and partial L, partial O. You see that from here, actually, everything here is I something, and here is partial L, partial O something. So that's why it's a dot product between them. You can derive it yourself if you write all of them out. And they can be simplified as this way. Partial L, partial F equals I dot product partial L, partial O. That's what we saw here. Partial L, partial F equals this. That's why it's this. You can derive it yourself. Not that complicated, but takes some time and patience. This is the first one. Second one is partial L, partial I. As I said, we need to get two things. Because partial L, the calculation of partial L, partial F also requires partial L, partial I. So we also need to get a partial L, partial I. That is here. We use the same, very similar deduction process. We will find that partial L, partial I, in this case, has a shape of 3 by 3 for the example that we gave in the previous slide, equals here. There's a new thing called full convolution. Full convolution is an operation that's very similar to convolution, but it's different. Here shows what a full convolution is. For example, if you want to get a full convolution of two things. One is the blue array, have 4 elements, 2 by 2. One is the yellow one, 2 by 2. The full convolution is like this. So you can see we have something that's like the padding, and it has a specific padding, and we need to move in a specific way to get elements. For example, the first one, you stack the two things up in this way, then you get a dot product of the overlap area. You will get the first, then the dot product is one number, would be the first element, one in the first row, first column. Then you do it in this way, you slide it, you get an overlap area, and the dot product or weighted sum will give us the elements in the position of first row, second column. So keep it going, you will get 9 elements, so 3 by 3. And F in this way is actually that's the filter array. We need to rotate it by 180 degrees. And between this one, we use this star sign to represent a full convolution. So we don't use a dot anymore. Okay, this is the conclusion. Next, let's take a look at the ReLU, or research-fied linear unit activation. So this one, active mathematical function of ReLU is very simple. It's just like this. So we have input and output. For input x activation, we let it go through the activation function. If input is greater than 0, then output is just x. But when it is smaller, equal to, or smaller than 0, then it's 0. Then you may ask, oh, why do we use this? Why don't we use a function like ReLU x equals x? Why don't we use that? We thought about that. Why just don't use y equals x as the activation function? If we do that, the activation function takes no effect, right? It does nothing to the input. It's the same input is same as output. That means we don't need the activation function. That's one reason. Another way of explaining it is that one major reason that we want to add in the activation functions is that we want to add nonlinearity to the model, right? You can think about the shape of the sigmoid and hyperbolic tangent function. They're not linear. Scratch everything in a nonlinear way, but they cause issue. So here it looks like linear, but here there's one thing here. That one gives us the nonlinearity that we want. In the meanwhile, you are not trying to scratch the data into that to end the saturation area, so that will help us to address the gradient vanishing problem. Or in another way, we can write this ReLU function as this. Now let's take a look at another layer, pooling. You saw that in AlexNet. You can see that pooling is actually one way of downsampling the image. It's just like, for example, you have big images, you don't want to deal with it, you want to shrink it. Pooling is something that we can use. The idea is very simple. For example, here if we have two major types of pooling. One is called average pooling, the other one is called max pooling. And in AlexNet, you saw the max pooling. Average pooling, what we do is that we need to have a size. Let's say that is 2 by 2 and has a stride of 2. So 2 by 2 has a stride of 2. The first window will be here, right? Next window will be here. So first will be this yellow one, next will be green one, third one with the blue one, fourth one with the gray one. And what is average pooling is that for the window that the pooling window is covered or focused, we just need to get an average of everything as the output. So for the first one, average pooling, first window 1, 3, 8, 4. The average of M is actually 4. You can do it yourself. Second one, 2, 5, 11, 6, 6. So this is forward. How to go backward? Backward, we do it in this way. For example, you get some gradient for this thing. We want to go to the previous layer. Now we need to do the upsampling, right? We know how we did in the forward pass, so we did do it in exactly the opposite way. When we do the average pooling, so for example, if we have 4, 6, 4, 2, we need to get back to what we had before we applied the average pooling. We just need to split this 4 into 4 pieces, 1, 1, 1, 1, and the 6 into 4 pieces, 1.5, 1.5, 1.5, 1.5. So that is how to go backward. Next, for the max pooling, this one is even simpler. So for first one, for example, 2 by 2 window is focused on this one. We just need to get a maximum value within all the elements inside the window that we focus as the first element. Because here we have a stride of 2, so we move to this green area. For this one, we get the maximum value here is 11. So that would do it. Now we go backwards. How to do that? There are different ways, and one typical way is that we want to see which element has the maximum value in the forward pass. Now we get 8. We just give 8 the value back to that maximum, the element with the maximum value in the forward pass, and all the other things will have a value of 0. Backward, we'll talk about the backward pass in back weight propagation. So for example, when you go backwards, you come here, right? Forwards, you have this. You need to apply the maximum pooling. You will get output, input, and output. When you go backward, we need to go from here to here. So this is coming from layer, the neighboring layer. So for this one, we need to originally in our forward pass, we have a shape of 4 by 4, and we plot this, we get a 2 by 2. Here we need to do it in the opposite way. We got 2 by 2, we need to get something 4 by 4. Okay. A strata is the step that you will make. No matter if you're talking about a convolution kernel, you're talking about a pooling window, we need to determine how big a step you make every time.
Okay. So in here, if we get 2 by 2 in 4 by 4, we have like 3 strides?
No, stride is 2. So 2 by 2, right? You first apply it here, right?
Okay.
Next, we need to determine how big a step. If this stride is 1, then you will move to here.
Okay.
But in this case, stride is 2, so you move to 1, 2. So it come here. So as I said, size of the window, the kernel, and the stride and the padding size will determine the size of the output.
Backward, when we do the maximum tuning in backward, do we have like information from the previous step so that we know we are putting like 8 here, we put in the correct position? Do we have information about that?
Yes. When we do the forward, because you have one forward pass, you have one backward pass, right? When you're doing the forward pass, then you will record the information. So when you come back to here to the same location, you know that, oh, in the previous forward pass, this one gives us the highest value at 8. So we need to give it back. And this is CNN. Next, I want to go through this quickly. For RNN, there are different architectures, and this is just one of them. In a very simple way, you can understand RNN like this. If let's say that if we are talking about a 3-layer RNN, 1, 2, 3, right? That's from a perspective of shallow artificial neural networks. X input layer, H hidden layer, and then we just get outputs. That is very simple. But what differentiates RNN from a 3-layer RNN is that we have one more connection like this. That will make things complicated. And previously, when we talked about ANN, we said that we have feed forward, fully connected, right? Every neuron in the current layer is connected to the neuron, all the neurons in the next layer, right? Now it's not the case. It's connected to itself. So that makes things complicated. And why is complicated? First, let's do one thing. Let's make it look a little bit more complicated. Let's have inputs, have a unit, have a weight, so we can get to the hidden layer. Then when it's connected to itself, it also, when we talk about shallow ANN, we see that for any connection line between two neurons, we should have weight, right? So here's the same thing. If H, the hidden layer, is connected to itself, we also have another weight, W. So you can see that we have more than one weight array, U. And when we go to the next layer, we have an additional layer, D. So we get output. Get output, we need to get the loss function. So we expand it a little bit. Loss function is obtained by comparing the true label and the predicted label. So one thing that we need to get familiar with when we're talking about RNN is something called unfolding. You can see that if we look at it this way, this is not easy to understand, right? This connection between the H and the itself. It's hard to understand. So how to do it? We can unfold it over time because we do it because it's good for this RNN. It's good to take care of time-dependent issues. Or not time-dependent issues, it's called time series issues. When you have data, for example, you speak something, your voice, the current status depends on the previous one, right? There are connections between different data points at different times. So this one, RNN is really good for that. What we do is that we unfold it over time. So let's say that this is the green one. The one in the middle is the current time step or current step. We call it the T. T, everything in this step is called XT, HT, OT, LT, and YT. Previous step, the red one, and the next step, the blue one. And now what connects the different steps is the connection between the hidden layer and itself. But now you need to imagine it this way. It's not H in itself. It's the H in the current time point and H in the previous and the future time point. And the way to connect them is just this extra weight. So you may ask, how can we do it, right? The way to do it is this way. Let's talk about the forward pass. We have XT. That's the input. for the current time point or time step, right? And you also have this W thing, or this H from the previous time step. If you solve the previous step, you should know the value of H, the neurons in this layer, right? You have this H, you have this XT, you have this W, then we use one activation function to put all of them together. We will get H for the current one. Later on, I will show you guys the equation. So you get H for the current one, then keep going, apply the V, we get output. Then we have another, this is sigma 1 and sigma 2. There are two activation functions. We have two activation functions, two layers here. First one is a little bit special because we need to apply to this one and this one. We get a combination of everything first, then let it go through sigma 1. And then sigma 2 is here. So we can keep doing this over time. Let's take a look at what really happens. Again, here you can see that for H, if you wonder how H for the current time step is obtained, H, we apply activation function sigma 1. The input is ZT, that's for the current step, right? What is Z? Z is just a combination of these things. U, B, they're the weights. XT and HT minus 1. Here, they are the input, and these are the weights, right? So we get this, get HT. Next, for HT, we just did what we did in the previous and in the very same way, but now the weight is V, and there's a C, threshold C, right? We get an OT. Now OT, you need to go through the second activation function to give us the tilde YT. That is the predicted label. Then the predicted label is compared with the true label, and at the current time, we get the loss function. But now we are doing this over time, right? We have multiple time steps. With multiple time steps, you will see that when we're talking about a loss, we're not talking about a loss at any step. We're talking about a loss for all the steps, right? So we calculate the loss at each step, then get the summation of them. That's the total loss. And some people say that if you think about, the network like this, if you take a look at the left, it only has 3 layers, right? Very simple. You may still think, oh, this is shallow. This is shallow learning. It's not deep learning. Why people think in RN is deep learning? It's because of this. When you unfold it over time, it's getting very deep, right? So that is the forward pass. Backward pass, we do it in a very similar way. There are just a few tricks. Let's first take a look at simple things. First, we know the L function. We know the partial L, partial Y, tilde T. That is the predicted label. It's just something like this. And for the loss function, so here I showed one example in the textbook. Sigma 1 and sigma 2 use 2 different functions. Sigma 1, sigma 2, that's a more sigmoid function. The derivative is just y times y minus itself, right? And the sigma 1, we use the hyperbolic tangent. Hyperbolic tangent function, the derivative of it is 1 minus the function squared. So I just give out something. Then based on it, we can get partial L, partial C, partial L, partial V first. If we get it back to the previous one, you can see that I used some yellow lines to mark weights or the model parameters that we need to update. V, C, U, W, V, right? All of them. So to update them, then you need to get a derivative of L with respect to V, or partial L, partial V, partial L, partial C, partial L, partial U, partial L, partial W, and partial L, partial V, right? All of them. So these two, they're the simplest one, partial L, partial V, and partial L, partial V, C. So partial L, partial C is, first we need to get this derivative over all the time steps. So you can do it in this way, partial L, partial C, we do it in a similar way like what we did in previous one. C is here, right? He is here, so to get the derivative of L with respect to C, we can get the derivative of L with respect to Y, then Y with respect to O with respect to C, right? Sorry, there's a typo here. This should be capital letter L. So L with partial L, partial YT, I just introduced is here. Then partial YT over partial O, there's only activation function between them. So just a derivative of sigma 2. Derivative of sigma 2 is here, right? And then just partial O, partial C. There's nothing between them, just 1. So if you do that, you come back to here, you will see that here is just this one, first one, here goes to here, And this one just comes from here. And for partial L, partial V, we do it in a similar way. And what makes it more complicated is to get the derivatives of L with respect to the other three, W, U, and B. To do that, one tricky thing is that because to calculate all these derivatives, we need to get one thing. That is partial L, partial H. Partial L, partial H, let's call it delta. For example, for the current layer, partial L, partial H, T, that is delta T. We can do it if we span it, also use the chain rule. We will eventually get this. You will see that this partial L, partial T for the current layer is related to the partial L, partial T in the next layer. So that is a tricky thing. You go backward. If you want to, for example, get a gradient here, the gradient will come from two things. One is come from the top, come from YT, comparison to YT and until the YT. The other one come from the previous HT plus 1 because there are also connections in two directions. One is the vertical one, this one. That's why we get this. So in order to get this, to calculate all the things, we first need to calculate all the delta T's. And one good thing is that usually the last layer, when we go backward, the last layer is the first layer we need to deal with, right? When we do the gradient calculation. In that layer, delta tau, let's say tau is the last step. This one can be calculated directly. So we calculate this one, then we go backward using this equation, layer by layer. We can get delta T for every layer. With delta T, you can derive the equations for the derivatives of L with respect to W, U, and B. So if you all get all the gradients, just R and N.
I think I'm falling for you.